That was beautiful.
That was tiring.
It was tiring. That was a very long flashback.
It was like 2 whole lessons of flashback.
2 whole lessons of flashback, hence Game Theory 3.
All right. Well, now that we're back, is there anything left to say, or did we basically cover everything?
Well, I think we covered almost everything, but if you recall from the flashback, there were 2 or 3 things we said were probably best left for another day, and it turns out that today is another day.
Not according to that video, right? If they watch that video now, then today is that day.
Every single person who watched those videos had to take several days to do it.
All right, that's fair.
At least emotionally. So I'm going to claim it's another day. And so we're going to talk about 3 things that we said that we wanted to talk about before. In particular, we're going to talk about solution concepts, and we're going to spend a little bit of time talking about mechanism design.
Oh, neat.
So let's start with some solution concepts. All right, Michael. So the first thing that I want to delve into is the notion of solution concepts. Now, we've actually talked about various solution concepts in Game Theory 1 and Game Theory 2, but we never actually, I don't think, sort of explained what they were or even pointed out that we were talking about different solution concepts.
So we need to talk about the concept of solution concepts.
That's right. We need to talk about the concept of concepts because it's concepts all the way down. All right, so here's the basic idea. A solution concept, or really just a concept, is basically just a rule for predicting how a game is going to be played. Right? So the one that we spent the most time on was Nash as a solution concept, and particularly Nash equilibrium. And so in the language of solution concepts, you're basically saying that there's a rule, there's a kind of formal process by which some particular game is going to be played, and that is you're going to play with the idea that you're getting into a Nash equilibrium. An equilibrium in general and a Nash equilibrium in particular. Okay, so does that make sense? So we talked about a few others and mentioned a few others. So we talked about Nash at length.
And what made Nash Nash was that all the players were playing in a way that they couldn't unilaterally improve, right? So they were doing best responses to whatever it was the other player was doing.
Right, but actually that wasn't really what made it Nash so much. Well, it was, but the big emphasis there is actually on equilibrium. The idea is that you were in an equilibrium because it was in no individual's best interest to move or to change in any way. And the particular kind of equilibrium we talked about was Nash equilibrium.
Okay.
So in fact, I want to talk about correlated equilibrium because that's a different kind of equilibrium. That's still an equilibrium, but is different from Nash, and in some ways turns out to be better under certain circumstances. And I'm going to even argue that, in fact, we use correlated equilibria all the time in real life. I'll give you an example of that at the end.
But is correlated so related to Nash?
Yes, it is, and in a very particular way, and I will tell you how in a moment.
Awesome.
Okay, so we're going to talk about correlated equilibrium because that's what I'm interested in, but I shall point out that there are several others. There's Trembling Hand, there's Stackelberg competitions, there's Subgame Perfect. We actually talked about Subgame Perfect, and when I say we, I mean you.
Right, in the context of multi-stage games, sequential games.
Right, Game Theory 2. But it's still a solution concept. So this notion of concepts and solution concepts is not limited to simple matrix games, but actually all of these work, whether the games are repeated or not.
Okay.
There's also Bayes-Nash. We did not talk about that. Coco, you mentioned Coco, but I'm not going to talk about that. And there are a whole bunch of others, and they just kind of go on and on and on. And I think when I talk about correlated equilibrium and explain how it's a solution concept and tie it back to Nash, you might see various other ways you might come up with solution concepts.
Okay. I mean, Trembling Hand sort of scares me a little bit, but are we going to go into any details about that in Stackelberg?
No, I am not going to talk about this. I'm not going to talk about this.
Okay.
I'm not going to talk about this. I'm not going to talk about this. And you know what? I'm not going to talk about this. I'm going to talk about that. Sound fair?
Sounds like a segue.
Sounds like a segue. In order to illustrate correlated equilibrium and why you would care about it, I want to first introduce a game. This is game theory after all. And this is the game of chicken. Are you familiar with the game of chicken?
I have seen the game of chicken on like movies from the 40s and stuff, or 50s or 60s. The General Tao part doesn't make sense to me, but the chicken part, it's like cars rushing at each other and like teenage, I'm going to say boys, deciding whether or not they're going to be chickens and swerve off the road, or whether they're going to be, tough guys and risk dying.
Right, that's exactly right. So the two versions are two cars going towards one another, vroom, 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 and who's going to swerve first? Although, what happens if they swerve in the same direction? Whatever. The other one is where they're both driving towards a cliff as fast as they can, and who's going to either dive out of the car at the last minute or turn their car away. And the chicken is the one who loses the girl because this is the 1950s.
The girl's in the car going over the cliff?
No, the girl's usually the one that starts the race.
Oh,
It's the 50s. It was a different time, Michael.
understand.
And what does that have to do with General Tso's? Well,
Or game theory for that matter.
well, it's a game, right? In fact, we can turn it into a game. And how do we know it's a game? Because I can draw a matrix. So I'm going to say that there are two actions here. You can either chicken out
Okay.
or you can dare.
Okay.
Okay? So let's just draw a matrix that captures that idea. So I'll just put it right here. Okay, so there's a matrix. You can either dare or you can be a chicken. Got
Okay.
it? Now, if both of you dare, then you both get 0 because that's what death is equal to in this world, 0.
I see. Nothing good ever happens again.
Right, nothing good ever happens again. You dare. So you both got the girl, but you both died, so it didn't really help.
You don't get the girl if you're dead.
That's probably true. Okay, so on the other hand, you could dare, and the other guy could chicken out, in which case you get 7, and the chicken gets 2. Why 2? Because you get to live another day.
You get to live, but you get to live in constant shame.
That's exactly right, which is worth 2.
Cool.
Apparently.
All right.
Or, of course, this is a symmetric game, so if I chicken out and you dare, it works the other way. And the other option is both chicken out. And that's a whole lot better than being dead. And it's actually better than living in shame alone because you're sharing the shame. But it's not as good as having dared while the other chickened out.
Okay.
Okay, so that sounds good?
Yeah, 6 seems kind of high, but I can live with that.
Yeah, it's math, Michael. It doesn't really matter. So it's a general sum game, and it's a matrix, and all this other stuff about cars and everything don't matter anymore because everything is the matrix. I'm going to give you a quiz.
Ah,
You love quizzes. You make me do them. You have to do them.
that's fair.
So what are the, in fact, this is not a part of the quiz, but I'm still going to make you answer a question. What are the possible combinations of strategies here?
Pure strategies?
Yeah, pure strategies.
I want to say DD, CD, DC, CC.
I'm going to assume you said what I thought you said, and I'm going to say yes, both can chicken out. One can chicken and the other dare, or both can dare. Okay?
Yeah.
Is that right?
Yeah,
Very good.
CC, CD, DC, and DD.
Right. I'm going to draw little boxes here.
Uh-oh, those look like quiz boxes.
They are quiz boxes. And what I want you to do is I want you to check off each one that happens to be a Nash equilibrium.
So each one independently is either a Nash or it's not a Nash. And if it's a Nash, I should check it.
Right. And if it's not a Nash, then you don't.
And check it, I mean put a check mark.
Right.
Okay.
We'll call this quiz the Monster Nash. I'm here all week. Okay. So you got
I'm
it? You
leaving
understand the
tomorrow.
question? This is the matrix.
Yeah, I
These are
think
the
I'm
things.
good.
Check the Nash quiz.
So basically, check if it's a Nash, and if it's a Nash, check it.
That's right. Check it if it's a Nash, and if it's not a Nash, don't. Got it?
Got it.
All right. Go. All right, Michael. So do you think you know the answer?
Yeah, I've been checking chickens and checking, and now I'm ready to check some boxes.
Okay. So you want to walk me through this?
Yeah, absolutely. So, all right, so let's look at the first one first.
Okay.
Chicken.
Mm-hmm.
Chicken. So it would be a Nash equilibrium if neither player would have any ability to benefit from switching strategies.
Okay.
But that's not true because if the first player switched to dare knowing the second player is playing chicken, the first player's score increases up to a whopping 7.
Ooh, 6 to 7. That's right.
So CC is not a Nash.
CC is not a Nash.
CD, on the other hand,
Let's see. CD.
good. That's the 2-7 thing. So the chickener
Yeah.
can switch to dare, and that will bring that player score from 2 to 0, which
That
is
seems bad.
worse. And the darer can choose to chicken, which would take that player's score from 7 to 6, which is also not good. So everybody's better off sticking with what they got. CD and by symmetry DC are Nash.
Excellent. Excellent use of symmetry there, Michael.
Thank you. So now DD, our good friend DD. So that's the upper left box. Well, we don't have to think too deeply in this case because anything's better than that box. There's no way that could be a Nash equilibrium because if either player switches, they get more than 0, which is better.
Okay, and that is absolutely correct. So then, what do we know about what is Nash? We actually have 2 pure Nash strategies here, Nash equilibrium, or 2 strategies that are pure Nash equilibrium, or some set of words like that.
I would say there are 2 Nash equilibrium pairs.
I think that's too much. Okay, so there's 2 of them, and they're both Nash equilibria. And so we're done.
Well, there could be others, right? We're checking the pure ones.
That's true, but actually I think it's worse than that.
Oh.
It does turn out, by the way, there's a mixed strategy, and I'll tell you what it is in a moment. But I think what's more interesting here is that in this case of the pure strategy, which I mean, they kind of suck, right? Basically what it says
I
is
see.
if both of you chicken out is bad, both of you daring is bad, or rather, they're not equilibrium. So if I know that you're chickening out and I was going to chicken out, I should dare, and so and the other way around. But the 2 things that are in equilibrium, neither one of them is kind of what I would call sort of stable in a meta sense, in that, okay, so here's what we'll do. I'll dare and you chicken out. How does that sound?
That sounds like our relationship.
Okay, well then let's try it the other way. You ask me.
Okay, I'll chicken out and you dare. How does that sound?
No, the other way around.
You dare and I chicken out. How does that sound?
No, the other way around.
I dare?
Yes, you dare.
That doesn't sound right at all.
Yeah, how dare
and you
you.
chicken out.
Right. Well, okay, that's a Nash equilibrium, and it's true that if we're both there, that's where we will stay. But I don't want to do that. This actually brings up a couple of points. One is something that we kind of brushed over in game theory 1 and 2, which is this idea that, yeah, there's a Nash equilibrium as if that solves the problem, but we never, if there are many Nash equilibria, we never kind of said how you would pick one over the other. And I think in this particular case, I would never, the person who's being asked to chicken out would not want to do that one. They would want to do the other one.
So what if we play a game to decide who gets to be the C and who gets to be the D?
Right. Well, I think that's a good idea. That's, in fact, really what sort of a mixed strategy is, right? You could, well, maybe it's not.
I was going to say, in particular, we could play a game of chicken, and whoever wins that gets to be the D, or the dominant player in this game of chicken. But then, of course, how you decide who's going to get to play which role in that game of chicken, and then it's chicken all the way down.
It's chickens all the way down, being eaten by turtles.
At every level of the hierarchy tastes just like chicken.
That's true. Okay, see, so it's just sort of not a big win. But there is a way, usually we get out of these kinds of things by coming up with mixed strategies. And it turns out there is a mixed Nash equilibrium here. I will not quiz you on it, however. I will just simply tell you what it is. All right, so here's the mixed strategy. The mixed strategy is that everyone just chooses to dare with probability 1/3.
Oh, really?
Yeah, that works out to be a Nash equilibrium. I will leave it as an exercise to the reader to convince themselves of that, but it does actually work out to be the case.
Huh. And so that means we both dare with probably 1/3, which means 2/3 of the time we chicken. So there's going to be some probability that we both chicken, some probability that I chicken and you don't, some probability that you chicken and I don't, and then the lowest probability is we both dare. Boom.
Right. So in fact, I'm glad you said that, because that's exactly how we would figure out how good a strategy this mixed strategy is.
Right.
So let's do that. So let me ask you a question. What's the probability that we both chicken?
4/9.
And how'd you get 4/9?
I looked at your notes. That's the problem with being in the same place when we're doing these recordings.
Well, I'm pretty impressed that you could actually read my handwriting. But
No,
sure.
I can not only not read it, but my eyes are old enough that I can't read it anyway, even if you wrote it nicely. So no, what I did is I took, if the probability of dare is 1/3, then the probability of chicken is 2/3, and we're independently choosing that. So the probability that both of us choose it is 2/3 times 2/3, or 4/9.
So what's the probability of one person chickening and the other person daring, in particular CD?
CD, so that's 1/3 times 2/3, which is 2/9.
And by symmetry?
9 seconds. Oh, sorry, 2/9. And then dare would be 1/9 because it's dare times dare.
Right.
And let's just double check that. 4, 5, 6, 7, 8, 9. Woo! Wait, no, not 1/3. The bottom thing.
Oh, thank you so much.
Okay. Oh, and so now we can figure out from this what our expected, let's say my expected reward would be for playing this Nash equilibrium.
Right. So let's say you're player 1. So this is you. So then if we do CC, so you're the row. What is your payoff?
6.
So we can just say 6 times 4/9. What's the payoff if you chicken out and I dare?
2.
2. And what's the payoff if you dare and I chicken out?
7.
And what's the payoff if we both dare?
0.
0. So we add all that up, multiply these numbers, add them, and what do we end up with?
You're asking me?
Yeah.
You're the one who can do arithmetic.
You're right. It's 4 2/3.
Really?
Yeah, we just did that by keeping the denominator the same. So that's 24 plus 4, which is 28, plus 14, right? Which is 42, plus 0. 42 over 9 is 4 2/3. This is actually pretty cool, and the payoff is 4 2/3 on average for you. And by symmetry, it's actually 4 2/3 for
Which
me.
I like better than both of us chickening out.
Right, both of you chickening out is...
No, sorry. No, that's better. I like better than me chickening out.
Right.
And then I only get 2.
Right, and so actually doing this, even though occasionally we will, in the game we'll both die, but of course we aren't going to die, we're just going to get 0 utility because all that other stuff doesn't really matter.
Okay.
We're going to do this. This is actually pretty good, right? This is a pretty good payoff.
Okay, I agree with that.
In fact, for either one of us, if we get in the short end of the stick for the CDDC, this is actually better for us.
That's true. The worst of us, or sorry, not the worst of us, that doesn't sound right at all, but the least fortunate of us is much happier with this outcome than the CD.
Right, and by the way, we're actually happier with this outcome than if we had uniformly randomly chosen between them.
And we're better off with this outcome than if we had done CD and then like split the winnings, which would be 4.5.
Yes,
which is
it's
a
the
little bit
same thing as doing half,
Okay.
multiplied by half, right? It's 4.5. 4.5 is less than 4 2/3. So right, those are in fact the same thing in this case.
Got it.
This is why it's something like a third and not something like a half.
Hmm.
So that's pretty cool. So this seems like a pretty good win, but I'm going to claim that we can do better.
Okay.
Okay. So let's remember this 4 2/3 and keep it around for a little while. And let me try to convince you that we're going to do better. Okay?
Okay.
Here's what we're going to do that's actually going to be even better than dying 1/9 of the time. What we're going to do is we're going to introduce a third party. So, here's Smooth, and here's Curly,
Yep.
and then here's my best sort of drawing of Chris, who's helping us with this class.
Oh, our course creator.
Course creator, Chris.
Developer.
I like course creator better because then it's CCC.
CCC.
That's like a good MC name.
The course developer is CD, which is on the screen.
That's true. Course developer, Chris. Okay, we'll do that. It does sound like a good hip hop name, though. You know what we should do? We should do some kind of rap of some sort.
You're going to have to teach me because I don't know how to do that.
Okay, well, we'll talk about it later. Okay, so we're going to put our little CD here, and he is going to stand between us. So he's going to act as a kind of go-between. And what he's going to do is he's going to make a decision for us of a certain sort. So here's the decision that we're going to have Chris do. Chris is going to write down 3 cards. One's going to say CC, one's going to say DC, and one's going to say CD.
3 cards.
3 cards, okay?
Yeah.
And he's going to shuffle those cards and then pick one of them. So in other words, he is going to uniformly randomly choose among C, C, D, C, and C, D.
Okay. Yeah. Okay, I get it.
So you'll notice that that's 3 of the 4 strategies.
It's 3 of the 4 strategies. Yeah, you're missing DD.
DD, which is the worst one.
Yeah, so you should put that one in.
No.
Okay.
Well, I could put it in and give it and assign it a probability of 0.
But I like that they're cards and they all have equal probability.
Right, they all have equal probability. So uniform choice. All right, so you with me?
I guess so.
Okay, so Chris randomly picks one of these 3 things. Neither of us knows what it is, and we don't know anything about what the other has, but Chris gets to pick up this card. And then what Chris is going to do is something very simple. Chris is going to inform one of us, perhaps both of us, one after the other, but Chris is going to, let's say for the purposes of this discussion, Chris is going to inform one of us of what that person's action is. Let's say Chris picks C, C. Chris will turn to me and will say, I want you to choose C. Now, Chris could also turn to you and say, I want you to choose C, okay?
And there's no conflict there because we can both chicken.
You can both do whatever you want to do. I'm just telling you, here's what the card says you should do.
All right.
Card says you should chicken out.
And he's going to force me to do that now?
No. Let me give you one more example, though, before I really answer that question.
All right.
Let's say Chris had accidentally, that is uniformly, probabilistically, chosen D, C.
Yes.
Then Chris would turn to me and say, the card says you should do D. Chris would turn to you and say, the card says you should do C.
But I would know that he was actually just making me chicken out because that's what people do.
No, that's because that's what the card says. Now, let me be a little bit clearer here, because I wasn't. These 3 cards are known to both of us.
Yep.
And we know that there's a uniform probability of getting any of those 3 cards.
And we trust Chris enough that he's not going to always give you the good thing?
Yes, he's going to, with probability 1/3,
Okay.
do that. Okay?
I trust Chris.
All right, I trust Chris. I mean, look at that hair. How could you not trust Chris? Okay, so Chris is going to pick one of these cards and then tell each of us what it is we're going to do or what we're being asked to do,
Okay.
but not tell us what the other person is being asked to do.
Okay.
So that's important. Got it?
Yeah, that's
Okay.
interesting because I can use inference.
You can use inference. So in fact, let me ask you what inference you should use. So
Bayesian inference. Oh, you didn't ask yet. I'm sorry.
I didn't ask it. So in fact, I'm going to, because you said Bayesian,
I didn't say Bayesian.
you just said Bayesian inference, I'm going to make this a quiz.
As punishment for saying Bayesian.
Yes,
okay.
how dare you. So here's the quiz. Let's imagine that Chris shows you C. What should you do? Should you do C or should you do D? And
Okay.
if Chris shows you D,
Mm-hmm.
what should you do? Should you do C or D?
So I have to figure out everything because those are the only two choices, right?
Yeah.
Okay.
This is how life works, Michael. Luckily, there aren't a lot of things.
All right. So let me just make sure. And so I know that it's a third, a third, a third. I know that Chris is actually going to show me my piece of whichever card he picks.
Mm-hmm.
And so that gives me the ability to probabilistically tell what you're going to pick, which means I can actually evaluate both of my choices of action and figure out which one's better.
So are you solving the quiz now?
No, I'm just making sure I have enough information to solve the quiz.
Do you have enough information to solve the quiz?
I think I do.
I think you do. Or as much information I'm going to give you anyway. So you ready?
Ready.
Go. Okay, Michael. So what's the answer?
I don't know.
Yes, you do.
I mean, probably it's going to be C and D because why would Chris tell me to do something that I shouldn't do? He's not that kind of guy.
That pretty much.
But
actually,
to
Chris-
figure that out, I have to figure out a lot of different values. So I need scratch area, like maybe on the
Do
upper
you?
right.
I bet you don't even need
Really? All right.
scratch area for at least
all right,
one
all
of
right,
them.
all right, all right. Well, if I'm shown D,
Mm-hmm.
then I know that Chris has C.
No.
Not Chris. Smoove.
Mm-hmm.
If I'm shown D, I know Smoove has C, and I can't do any better.
Right.
So I'm going to take that. So show me D. I'm going to do D.
Done. That is correct.
Well, that's assuming that you're actually going to do what you're told. Which
But this is interesting, right? You'll notice that this whole game is symmetric.
Sure. Okay. So now I have to do the other box.
Yeah, so what's good for the goose is good for the gander. What's good for Smoove is good for Curly. So certainly if I saw, or Smoove, because this isn't me, of course, saw D, you would still do D, right?
Kind of looks a little bit like you.
It's a little bit like me.
Yeah. Right. So again, I need to figure out the top box.
Let's figure out the top box. You think you need scratch area?
Maybe. All right. So let's think of it this way. So if I'm shown a C, actually, I guess it's 50-50
Yeah,
what the other player is going to be shown, what Smoove is going to be shown.
that's right. If you're shown a C, then it's got to be one of these two cards. And so Smoove will see a C half the time and see a D half the time in that situation.
So, and that means that my payoff for doing C
Okay, here, I'll help you out here. Your payoff for doing C.
is going to be the average of two of the boxes. Which boxes? The CC box, the bottom right,
Mm-hmm.
and the DC box, which is the one above it.
Um,
Well, let's think of it this way. So I'm chickening, and you're choosing whether or not to dare or not.
mm-hmm.
If we both chicken, I get a 6. If you dare and chicken, I get a 2. So that means 6 and 2 is 8, divided by 2 is 4. So I average 4 for chickening.
So with probability 1/2, you'll get a 6. With probability 1/2, you'll get a 2, and that happens to be 4.
Good. All right. Now daring, if I dare, you are randomly either daring or chickening. If you dare, I get 0. If you chicken, I get 7. So on average, that's 3.5.
So which should you do?
Oh, I'm better off chickening. Look at that.
And by symmetry,
When I am shown D, you're also going to be better off chickening. So I should actually do D. So I can actually kind of predict your behavior as well.
mm-hmm.
We should all just do whatever Chris says.
Exactly, which I'm sure Chris loves to hear. It's not going to happen, but I think Chris sort of would like to hear that. So what have we just done? We have just created a situation where if you're told to do C, you will not change your behavior. If you're told to do D, you will not change your behavior. And the same is true for me. What do we call that?
It's a kind of equilibrium.
It's a kind of equilibrium. And in fact, it's what we call a correlated equilibrium.
Ah.
Now, why is it an equilibrium? Well, it's an equilibrium because there's no need to change given a setup. And it's correlated because we have a sort of information item, a bit, a thing, an object, in this case, cards, or Chris representing the cards in this case, where we can associate what we've got with what you likely have, the decision that we want to make with the decisions you want to make, and that correlates it.
Interesting.
And this creates a wonderful little incentive to do the right thing in this case, or at least to create an equilibrium. Now, we were very particular about this. If I had thrown in the fourth card and I had made them all say 1/4, 1/4, 1/4, we basically would be back where we were before. So constructing these actual distributions and coming up with the right ones, is something that requires a little bit of work. But I just wanted to show you here that it can be done. So we have created a correlated equilibrium by creating this Chris thing that tells each of us what we ought to do, and we know a little bit about how that process is done, and so we're going to do what Chris asks us to do.
That's really cool. I think I have some questions, though.
Ask me some questions.
You said things sort of fast, but just to be clear, you're saying that there could be other distributions on the cards other than uniform that also have this property, this correlated equilibrium property?
I suppose there could be. I actually haven't worked that out.
So you didn't pick a half by solving it out and there was some unique answer. You just kind of worked. Right, sorry, a third for the 3 cards. You didn't solve for that. You just picked it and it worked.
I happen to do that, yeah.
And then there was a question of, am I better off with this than doing the mixed equilibrium?
Well, that was a question that we started with, yeah. So I guess we should answer that question. Would you like to answer that question?
Yes.
Let's make it a quiz.
Okay.
All right. Okay, Michael, so here's the quiz. What's the expected value of the correlated equilibrium?
Expected value, were the expectations taken over the card choices?
Yeah, that thing.
And what I get in those different cases. I think I can do that.
I think you can too. I have faith in you. So are you ready? Do you have enough information? The answer is yes, by the way.
Yes, by the way.
Excellent. Okay, so go. Okay, Michael, so you ready? Do you know the answer or how to compute the answer?
Well, I feel confident that I know how to compute the answer. I was trying to do it in my head, but then, math. So 2/3 of the time, Chris is going to tell me to C, to chicken.
Yes.
And we worked out, it's on the top of the screen there, that I score 4 on average in that case. So I would write down like 2/3 times 4.
Okay, so 2/3 times 4.
Plus 1/3 times what I get in the case where I'm told D, which we did clearly last time and got 7. So it's 1/3 times 7. So,
Okay.
that's now you can see why I was having a little trouble doing it in my head. So 8/3 plus 7/3 is like 15/3, which is like 5.
That is correct.
Yes.
Good job.
So that's so cool. So that's not quite. Actually, we're still better off by both chickening out. But maybe we have some dignity this way. We have less utility.
Wait. 2 things. Let's point this out. You skipped something.
I did.
5 is greater than 4 2/3.
5 is greater than 4 2/3. So we're better off following this than choosing the stochastic equilibrium. Oh, which was the only fair one that we had at this point.
Right.
So this is a way that we can actually both do the same and do better than the other way that we can both do the same.
Right. So this is better than that. But you pointed out that we're still better off if we both chicken out.
Yeah.
So why won't we both chicken out again?
In the case of this particular
No, just in general.
equilibrium?
Why would we not both chicken out? You just said we're still better off by both chickening out. And you're right, because 6 is greater than 5, which is greater than 4 2/3. So why won't we both choose to chicken out?
I'm not sure. It seems to me that Chris could tell us our cards and we could just like yell over the wall, we're better off just chickening out. Don't D on me.
And what's going to happen if I know you're chickening out?
You're going to D on me.
I'm going to D on you.
I see. I'm going to not take that risk.
Because it is not an equilibrium.
I see.
So what's nice about this is that it's better than this. 5 is better than 4 2/3.
Oh, I see. I see what you're saying. You're saying that 6/6 is a fine score, but it's not an equilibrium.
Not an equilibrium.
And 5/5 is a pretty good score for an equilibrium. It's pretty fly for an equilibrium.
Yeah, that's exactly right.
That's cool.
Yeah.
So we got this power out of the magic that is Chris.
We got the power out of the magic that is Chris. He is our little correlated thingamajigambob, our object that provides enough information to the players so that they know enough about what's going on to make a decision that's better than both of them. But again, remember what's important here, right, is that in the correlated equilibrium case, neither side knows what the other is doing, but knows something about what they could do because they know something about the card.
Bayes rule.
That's right, because given the card, I know something about the others.
Right. Given my card, I know something about your card. Okay.
Right. Okay. So correlated equilibrium better than Nash equilibrium. Now it turns out in this particular case, it turns out that there are some neat little facts. But before I go in this neat little set of facts, I want to point out to you that we do this all the time. That Chris is actually a stand-in for objects in the world that provide information all the time.
I find that hard to believe.
So let's go back to our original game of chicken.
In particular, I just met Chris for the very first time yesterday, so it can't be that common.
No, this is the ideal Chris. So do you know, in fact, what the ideal Chris is in the game of chicken?
The ideal Chris in the game of chicken would be like a random number generator that is on the street yelling cards at us?
Close. We actually have that. Do you drive, Michael?
I do drive.
I'm going to
I don't drive a car that's as nice as your car, but I drive just fine.
I didn't ask you for a value judgment about how well you drive, but you do drive, right?
Yeah.
Okay. And I'm going to claim that every day when you drive, you're actually playing a game of chicken, especially whenever you come to an intersection.
I'm pretty sure my payoffs don't look like this.
Well, it's just the wrong unit.
All right, but okay, all right. So I will, okay, so when I come to an intersection, it is definitely the case that I can either stop at the intersection or I could go through the intersection,
right.
And I'm better off going through it, than I am just stopping and waiting. Mm-hmm. And I'm really bad off if I go through, but at the same time someone else is going through.
Yep, you're basically playing chicken and dare all the time, except instead of going at each other directly, you are going at each other at, let's say, right angles for most intersections. And the good case is I get through without having to stop. The bad case is I wait forever while people go through. And the even worse case is we both go through it once and we crash. This is exactly the game of chicken. So how do we avoid this?
Well, we look at each other.
No.
There's a stop sign there.
And what is the stop sign there for?
Make me stop and look.
It's to tell you what to do.
But it always tells me the same thing.
Yes.
It's always telling me to stop.
But we know what the rules are. The rules are with a particular stop sign. If you stop, you need to stop and look to see what else is going on. We have a more generalized form of the stop sign, though, in busy intersections in the middle of cities.
You're thinking of traffic lights.
That's right.
Now, traffic lights aren't random.
Well, it's sort of random in the sense of when you show up to them.
Oh, interesting. And so it gives me one of two signals, basically dare, meaning go through the intersection.
That's green.
Or chicken, meaning stop, meaning wait at the intersection.
There's also one in the middle, by the way, which means go faster. But that's not really important. Let's just stick with the red and the green one. So what is this traffic light telling you?
It's telling me my half of the strategy. We're correlating our behavior with the other drivers.
Right, because when I see red, what do I know the people coming the other way see?
I don't know. I guess if I see green, I know that everybody else has the red, so it's clear for me to go.
Right.
So that's the really important thing is it won't show us both green.
Right. If we have a chance of crashing.
Oh, and that's just like showing us both D,
Yep.
which is the thing that doesn't happen in the list of cards.
That's exactly right. So in fact,
crazy.
All of this is just a bunch of probabilistic blah, 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 blah. It's really just a traffic light.
Huh. Okay.
And these things are very important. And we all sort of obey these things because it mostly makes sense. Even in weird countries like the UK, where you're allowed to run through a stoplight, or at least to go through a stoplight, instead of having to sit there forever, at certain times of night when no one else is coming, you still stop because the red light tells you to stop because that's the right thing to do. And if you don't do it, there's chaos. The point here is that we create objects in the world that provide each of us with some information about what others are doing, which allows us to play these kinds of games without necessarily crashing into one another. We've come a long way since the 50s.
I see.
Okay, so let's review quickly. Okay, so by way of wrapping up on this, let me just point out 3 quick facts about correlated equilibria.
Cool.
Okay, so here's the first one. Correlated equilibria, or CE, as the cool kids call them, can be found in polynomial time. So this is a good thing. So even though I didn't, tell you how I found the 1/3, 1/3, 1/3, 0 correlated equilibrium in the previous example, you can find that in a reasonable amount of time. I found it in even more reasonable amount of time, which is I looked up the example and I wrote down the numbers, which is also polynomial. Okay, in fact, it's linear. Okay, so...
And that's not so true of Nash equilibria, right? Nash equilibria are hard to find.
Yes, they are, which is unfortunate.
No, but okay. It's a nice advantage of correlated equilibria.
That's true. But Nash sounds so cool. Well, in any case, okay, the second fact is all mixed Nash equilibria are in fact correlated. So this means that correlated equilibria exist. That comes from what we discussed before, that there's always at least a possibly mixed Nash equilibrium.
Cool.
And of course, pure Nash equilibria are themselves mixed Nash equilibria. Therefore, correlated equilibria exist.
Gotcha.
Okay. Finally...
Wait, you pure in the sense of, the original definition of.
Right, exactly.
Okay.
And then the third one is, and this just kind of follows from probability, all convex combinations of mixed Nash equilibria are in fact correlated.
Whoa. Okay.
There's a lot there, and we could talk about it forever, but the basic idea is that correlated equilibria are kind of cool, traffic lights are not a bad idea, and coming up with them isn't impossibly hard. Unlike all that other stuff you talked about before with POM-DPs where they're undecidable and life is terrible, at least here we can actually find pretty good correlated equilibria, or at least we can find correlated equilibria.
That's a relief.
It is a relief. Okay, so I think I'm ready to go on to the next thing. Here's sort of the last thing. I guess I'm kind of done with solution concepts, right? So I said that we've done Nash equilibria. We did subgame perfect. We have now done correlated equilibrium, and we're not going to talk about any of these other things. So I guess we're done.
I was really hoping that we would talk about at least the cocoa thing. I think we said in the summary that there's more to say about that.
Well, there's more to say about everything, Michael, but that doesn't mean that we have to say it. Just because we can do something, it does not follow that we should.
So, but cocoa is interesting in some of the same ways that correlated equilibria is interested in. Sort of goes a little bit beyond it in some ways. Like I feel like it would kind of round out the story really nicely.
Okay, well, I'm a big fan of story rounding outing, so
with TD, MD, TD.
I am more than happy to let you do that. Would you like to?
Oh, sure, yeah, I can do that.
Okay, well then here's the pen.
Great. So if you just don't mind. Great. Now I will take it from there. All right, awesome. I get to tell you about COCO values. So COCO stands for cooperative competitive values.
COCO stands for that?
Well, the COCO part of COCO value stands for cooperative competitive.
Okay.
And this is an idea due to Kalai and Kalai, because you need as many of those as you can get.
Mm-hmm.
Here is an example of COCO values that features some people that you may recognize. So this is Curly and Smooth, and the bananas. So Curly and Smooth would like to get bananas. Turns out Curly is too short to get any bananas.
So true.
And Smooth is tall enough to get 2 bananas.
Yeah, that's about right.
But if Smooth stood on top of Curly's head, then he could actually get 4 bananas. He could reach these 2 additional high bananas.
Oh, so it's like a Tuesday.
So let's set this up as a matrix game. Here's a matrix version of the game. So this is addressed to you, and you have 2 choices. You can just reach for the bananas yourself, or you could stand on top of my head and reach the other bananas.
So you're my friend in this.
Sorry, Curly. You could stand on top of Curly. Not you. I mean, Smooth can stand on top of Curly's head.
Okay.
And Curly has the choice of either allowing that to happen or not. Okay?
I like this game.
Yeah. Believe it or not, I did not make this up for the purposes of this class. And so we can ask some questions about this. So, for example, what's the Nash?
Oh, I'm sorry. You're actually asking me what the Nash is? I guess
It's a rhetorical question, except it's not rhetorical. It's just a question.
Pure Nash?
If you can find one, sure.
Okay. Well, is there a pure Nash? I mean, I've just seen these numbers for the first time.
Yeah, but you shouldn't. Okay, sure.
So I can just ask the question. All right. So if we do don't boost and reach, would either want to move? Well, it doesn't really matter if you go from reach to climb. You get the same value.
Right.
And it doesn't matter if
you change. Sorry, you. Right, you. Smooth. It doesn't matter to Smooth.
It doesn't matter to Smooth if you're in don't boost reach. And if you're in don't boost reach, it also doesn't. Wait. No, I'm sorry. Take that back.
It does matter.
It does matter. I'm reading the numbers backwards. So the first one is for Curly, and the second number is for Smooth.
See, I put them in the same order as where they're standing.
No, and that makes perfect sense. So if you have 0, 2, so then if we're stuck on don't boost and Smooth can move from reach to climb, Smooth would not do that because you're going from 2 to 0.
Mm-hmm.
Meanwhile, if we're in don't boost reach and Curly can change, and Curly would go from 0 to 0. And that doesn't really make a difference. So I guess don't boost and reach is a Nash equilibrium. So let's see. I think there's a symmetry thing there. So we know don't boost and climb is not a Nash equilibrium.
Good.
For the same reason that 0, 2 is 1. 0, 0 is not, because I'd be going from 0 to 2 if I were Smooth. So there's no point worrying about that. What about boost and reach? Well, let's see. That's 0, 2. And so Curly doesn't need to move. It doesn't have an advantage to moving from boost to don't boost. But Smooth would want to move because you'd be going from 2 to 4. So that is not Nash equilibrium.
Okay.
Now let's look at boost and climb. So boost and climb, let's see, it's 0, 4. So if I went from boost to don't boost, I would still stay at 0. And so that doesn't help Curly any. And I wouldn't move from climb to reach because I'd be going from 4 to 2. And so therefore, that is also a Nash.
All right. Now, which Nash equilibrium do you think would be more beneficial?
Well, for Smooth, it would definitely be boost and climb.
Yeah. What about for, like, the society of these 2 people? Like, if you just add up the total retrieved bananas.
So that would be 2 versus 4.
Yeah.
So in fact, again, boost and climb would be, on average, more beneficial.
On average.
Or, the sum for the society.
Yeah.
Sum,
right.
average is all the same thing.
Right. But it sort of doesn't matter to Curly, but it would matter to Smooth. And it's also the case that to Nash, it doesn't really matter. Both of these are Nash equilibrium, so they're both perfectly acceptable from a Nash equilibrium sort of point of view.
Yeah, and this is like the example that I did with chicken, where you have 2 Nash equilibria, and they're both kind of equally good from Nash's point of view. Although in that case, they're very different from the 2 players' point of view. Here, I suppose, either way, Curly gets nothing. So really, it's just about making Smooth happy. I like this game.
So, okay, sure, fine. So that being said, can we say anything about correlated equilibria?
I mean, I'm sure we can, right? We can, any mixed Nash equilibria is a correlated equilibria, but I think this one's a little different right here, right? Because no matter what happens, Curly gets 0.
So that means that Curly, like anything's going to be equally okay to Curly.
Right.
So Curly's not really going to participate in the equilibriumness or lack thereof.
Right. So really, this is all about getting to boosting and climbing.
Yeah, though I think you said that any convex combination of a Nash is a correlated equilibrium.
That's right.
So it should be everything like 0, 2, 0, 2, 1, 0, 2, 2, 0, 2, 3, 0, 2, 4, 0, 2, 5, 0, 2, 6, all the way up to 0, 3, 0, 4. We know that all those have to be Nash.
Right.
Or values of correlated. There has to be a value of some correlated equilibrium that is like 0, 3, for example. Maybe this is not a great example, but I want to say, if we were in this situation, what would we actually do? I mean, if it really is kind of, if we're doing
don't boost reach, for example, what would you do to encourage me to maybe participate in the other Nash equilibrium?
I guess I would just state that's what we're going to do, and you'd have no reason not to do it.
Yeah, but I'd be like, no, I have no reason to do it either.
This is true, but since all the utilities are inside the matrix, you might as well just do it.
I might as well not do it.
Well, you got to do something.
Well, I'm going to don't boost.
But why? They're both the same. They're both 0.
Okay.
I thought you wanted to make me happy.
I didn't. You have. That's not game theory. Me making you happy is not game theory.
Well,
Game
not my
theory is
theory.
about utilities. So, is there anything that you could do to change the utility for me?
Oh, sure. I could offer you a banana.
Aha! Could share. Yes. And so the essence of what happens in Cocoa values is that we're going to talk about making side payments. So the punchline is going to be we're going to do this thing that actually benefits us mutually, like the sum of the payoffs is maximal, and then we're going to dispense the spoils, right? We're gonna get as many bananas as we can, and then give them out in a way that's fair, sort of. I mean, a priori, it might not be so obvious what would be fair. Like maybe I would say I'd hold out for no, I'm not going to give you a boost unless you give me 3 of the bananas. You can keep just 1. But it's going to turn out in this particular case that 1 banana payment actually is justifiable.
That's cool because that's what I was thinking. I was thinking,
Yeah.
look, man, I'll give you 1 banana.
Now, what if this was 40? Would you still feel like 1 banana would suffice?
For me, yeah.
But for me to actually give you a boost,
I guess you would expect more.
maybe more.
Yeah. So, I mean, I don't know that I really thought this through, but when the number was 4, it's like, look, I can get 2 if I want to.
Right.
So really, this is about why don't we split the extra benefit?
There, nice. Okay, and that is a really powerful intuition for understanding how these things go.
Okay.
So here's the actual definition of Cocoa values that we're going to use, and that come from the Collide work. So the Cocoa value of a game is going to be defined like this. Let's imagine that we've got a general sum game. The notation I'm going to use is U is payoff to you,
Okay.
and U bar is the payoffs to not you, right, the other person.
Yeah, that makes sense. Although I like that you use the bar because that means compliment. So you're
Yeah.
saying we compliment each other.
This has nothing to do with me.
You said you.
It has something to do with you.
Okay, now you're just confusing me with your pronouns.
All right, sorry. So I should have called the other matrix I. No, wait, that's not going to help. All right, so so the general sum game that we're actually solving here is U bar, and why don't we just compute, say, a Nash equilibrium of that general sum game? Well, there's a bunch of reasons. One is that they're hard to compute. Another is that maybe it would be indifferent to getting those extra bananas and sharing them around.
Right.
So what we're going to do is we're going to define the Cocoa value, and we're going to use the Cocoa value to actually divide the spoils. So here's how the Cocoa value is defined. We're going to take the general sum game U bar, and we're going to turn it into sort of redistribute all those utilities that are in those 2 matrices to create 2 matrices, one that's purely cooperative and one that's purely competitive. We're gonna create one game by thinking about the average values that the 2 of us would get for each of the different possible joint actions.
Sure.
Right. So imagine that we'll get whatever we get and then we split it evenly.
Okay.
All right. That's very cooperative.
That is very
Right?
cooperative.
And in fact, mathematically, it's just U plus U bar over 2. It becomes the matrix payoff that we're both going to abide by.
That seems reasonable.
Purely competitive version is for us to look at the difference between the utilities that we get and split that in half. Right. So it ought to be the case that if we add these 2 matrices together, U plus U bar over 2 and U minus U bar over 2, we get U from my perspective, from U's perspective, and we get U bar from the perspective of the other player. So we recover those same utilities from the general sum game. But we've redistributed them into these 2 matrices, one of which is purely cooperative. We get the same payoffs. And the other one is purely competitive because one of us is playing U minus U bar over 2, and the other is playing the negation of that, which is U bar minus U over 2. Right? So what's good for you is bad for the other player and vice versa.
Okay.
In particular, this is a zero-sum game now.
Right. So in fact, I was actually going to ask, what would happen if you were playing a zero-sum game? Then U plus U bar would always be 0. And in fact, this would say you should do minimax on the gap.
U plus U bar would always be 0. Yeah, once we've redistributed these into a new U and U bar, yes. And so what's the Nash-like thing, what's the equilibrium-like thing to do when we're playing a purely competitive game? And that's to take minimax. So we're actually going to compute the minimax value of that game, and we're going to compute the maximax value In other words, which cell has the highest sum payoff or average. You say sum and average is the same. Find the cell that has the largest thing and say, okay, well that is also a Nash equilibrium of the purely cooperative game. Because if we choose the square that has the highest payoff out of everything, then we're going to have no incentive to switch to something else.
That's right.
How do we compute the cooperative equilibrium?
You just replace all the things with their sum and take the biggest one.
So it's like taking a max of all the cells of the matrix.
A max of all the of the new cells of the matrix.
Of the new matrix, that's right.
Yes, that's right.
And what about minimax?
Wait.
Do you not remember how to do that?
No, I do. I try to remember which one is which. Let's pretend I don't remember how to do it.
Anything that's not a dynamic program is a linear program.
Truer words have never been spoken.
Because it's all about programming. All right, so in particular, you can set this problem up as a linear program and solve it in polynomial time. So this is efficient, at least in a formal mathematical computer sciencey kind of sense. And so is this.
Right.
So we took a game that we actually don't know how to solve because computing a Nash equilibrium can be really hard. And we've broken it up into two, again, just by redistributing the wealth, redistributing the utilities, we actually split it up into two games that are the same amount of utilities being spread around, but we can actually compute the equilibrium value for both of them really easily, and then we're just going to add them together.
Okay. And then what does that tell us to do?
Good question. So the way that this actually plays out, it's easier to see in the context of an example. So let's go back to our example from the banana game.
Okay.
So here's the U and the U bar matrix from the banana game. This is, I wrote them backwards, didn't I?
Doesn't matter.
So there's one player who gets 0 no matter what.
Yep, that's the friend. That's Curly.
That was Curly before. And then there's one who can get either 2, 0, or 4, depending on which cell they end up playing. And we said that the Nash equilibria were these two corner cases, the 2 and the 4. So that gives us the purely cooperative game, which is the average of the payoffs for the two players, which we're going to compute the value of using Maximax. And the purely competitive game from the perspective of the U player, so U minus U bar over 2, which looks like this. So we're going to try to resolve the value by minimax. Then there's this same quantity from the perspective of the U bar player. So it's just the negation of that one, but we're going to compute the minimax value for each of these different games. So from the perspective of the U player, what's the max value and the minimax value for these games? So let's start with this one. So what's the maximizing value?
It's the thing you're pointing at.
And that's the case where U plays the second row, and U bar plays the second column, and they get these payoffs.
Right. We get 4 bananas.
4 bananas that we're going to divide amongst us.
Sure.
So the minimax value, so what's the score that the row player, the U player, the maximum score that it could get for itself?
-1.
You get a -1. Right. So how does it do that? By picking this cell, the top row, because the top row, if you're trying to minimize my gains, you're going to choose the left column if I choose the first row. If I choose the second row, you're going to choose the right column. I'm going to do even worse.
Right.
So the best thing I can do is choose the first row.
And I know that, so I'm going to choose the first column.
Good. And if we negate that, we get a completely analogous analysis.
Right.
So which column do you choose, this or that, given that you're trying to maximize your value? It would be great if you could choose the second column, but I'm trying to minimize your value, so I'm going to choose the first row if you choose the second column. So the safest thing you can do is choose the first column, and I'm going to need to choose the first row to keep you from switching to go down to that 2.
Right.
All right. So from the perspective of U, the cocoa value is the sum of these two things, which is 1. And from U bar's perspective, the cocoa value is the sum of the min-max game and the max-max game, which is going to be 3.
Right.
Now we have to define side payments. So U's side payments, P, is the cocoa value from U's perspective minus the value that U gets in the equilibrium, which in this case is 0, but in general it's whatever the utility is according to U of the utility maximizing joint action. And the side payments for U bar are the cocoa value from the perspective of Q bar minus the value that U bar gets in the utility maximizing joint action. So in this case, that's 1 for U minus how much does U get in that game? 0.
0.
So it's going to be 1.
Mm-hmm.
Whereas from P's perspective, the cocoa value is 3 minus the payment that U bar gets for playing the utility maximizing action, which is 4. So we get -1.
Oh, and that makes sense because it better be the case that they are opposite and equal. You have to transfer. And now you've answered my question. Who gets to transfer money from one to the other?
That's right. So the U player is going to get 1, and the U bar player is going to give 1, and that's the 1 banana exchange. So to wrap things up from the perspective of cocoa values, we learned a couple things. We learned that they're efficiently computable because we can do it with a simple maximization and a linear program added together.
Mm-hmm.
What we end up getting is a behavior that's utility maximizing for the 2 players, and then they split it up afterwards.
Mm-hmm.
You can think of it as actually decomposing a game into a sum of 2 games, one of which is purely cooperative and one is just purely competitive. We're just kind of shifting around the utilities, but we do it in a way that leaves us with 2 really nice games to work with. The result of that is unique. There is a unique cocoa value for each of the players. It's unlike a Nash where there can be multiple different possible values depending on which Nash you pick. There's just the one cocoa value. It's very convenient.
That is convenient because that means there's an answer.
There is an answer, yeah. We've discovered that, in fact, you can generalize this notion not just to matrix games like we talked about, but actually to stochastic games in general. And we get an algorithm that we call CocoQ. CocoQ is a Q-learning-like algorithm that uses cocoa values to learn a strategy in a stochastic game where they actually can make little side payments after each move. So the 2 players move, and then they divvy some stuff up, and then they move again, and they divvy some stuff up. And those side payments actually end up being sensitive to issues like we just got really unlucky, or I'm about to take an action which is very risky. And so, you're going to have to pay me to take that action. And the payments have these nice interpretations in terms of kind of paying people for taking risky actions and giving them the benefits of things. It's neat because this actually converges, this Q-learning algorithm converges, in spite of the fact that the operator, the cocoa operator, is not a non-expansion. We've talked about non-expansions in the context of generalized Q-learning. This is a case where that analysis actually fails, but there's a different analysis that you can use to show that the algorithm actually converges. So that was surprising to me anyway. I spent a lot of time worrying about non-expansions, thinking that they were the answer to everything.
Yeah, they answer to everything except for things that are
just not this thing.
Yeah, cuckoo for Cocoa Puffs.
One thing that's worth pointing out is that what you get at the end of this is not necessarily an equilibrium, which is to say, once we've computed what the cocoa values are, I might not want to play that game. I might not want to do the side payment. I would rather get my value in a Nash equilibrium or something like that. And so that means that to really make this work, this side payment mechanism has to be binding. They have to agree in advance that whatever happens, we're going to do what the cocoa value says we should do. And it's somewhat beneficial, but making this binding agreement in general is not beneficial. It could be, for some players, they'd rather just not do it. So it's not an equilibrium in the same sense as like Nash and correlated.
So we're going to have to hire police officers.
We're going to have to hire police officers to divvy up our bananas.
Okay, so just like real life.
So thank you for letting me have a chance to come and discuss cocoa values, which otherwise we would have not gotten to.
But I like it. So should I learn from this that basically we should always be doing cocoa values or cocoa? Yeah, we should always be doing cocoa and, hiring police officers, make things binding?
Boy, I don't know. I mean, in general, you tend to get a higher sum of values from the cocoa values, so paying the police officers probably makes sense. So it might be worth hiring them. For specific games, it's not necessarily true. It doesn't necessarily kind of fit. Another problem with the notion of cocoa values is that it doesn't really generalize if you've got more than 2 players. So this is specific to the 2-player setting. If you have 3 players, you can't split it into, 3 matrices, one of which is cooperative, and another which is competitive, and the other which is, combustible.
Well, what if you did all pairwise games? You'd have to get extremely lucky.
It doesn't seem like there's a natural extension of this that works for more than 2 players. I mean, it's an open problem, and so no one's shown that you can't do it. So, that could be a homework problem.
Oh, yeah, that's cool. And then anyone who gets PhDs for everyone.
PhDs for everyone. Wouldn't that be nice?
That would be nice. Okay, so we've gotten through cocoa values. That's good. So we worked together, and now we've done 2 solution concepts in some detail.
Yeah.
Everybody wins.
That's the thing. And now we can actually do side payments to kind of divvy up afterwards.
So what are you going to give me?
I am going to give you back the pen so that you can wrap up the section 3 on game theory.
Sounds good. So now that I've got the pen back, we're going to wrap this up by talking about something we promised to talk about at the end of last class, which is mechanism design.
Cool.
right? That seems reasonable, right?
So it's like mechanical engineering.
It is not like mechanical engineering, except in a very abstract and analogy sense.
Okay.
So what mechanism design is, it's kind of the art, the science, and the engineering, dare I say it, of creating games to elicit certain kind of behavior. So far, what we've been talking about with all our solution concepts and all the things that we've been doing in game theory 1, 2, and 3 so far is we've talked about what happens when we play games. And, at least stepping back a little bit, what we get when we play games is we get certain predictable behaviors. And those behaviors are natural. They're Nash equilibria, or maybe they're correlated equilibria, or maybe they're Coco, whatever, equilibria, and other things we haven't talked about. But here what we want to do in mechanism design is we want to make a game instead of just play a game, but again with the end goal of getting some specific behavior. Okay? Does that make sense?
It feels kind of like inverse reinforcement learning in that we're going from the behavior that we want to a game that would make that behavior, whereas in regular game theory we go from the game to the behavior.
Okay, I like that. In fact, I like it so much, I will draw the arrow that way. So here we have a behavior we want, and we're going to come up with a game that would actually lead to that behavior. I like that. And then once we've made a game, what will happen is we will get people to play that game, and then that will generate the right behavior.
Nice.
Okay, cool. So it's like a sort of cycle of life thing. Does that seem reasonable?
Yeah, it's not a cycle though, but sure.
Now it's a cycle.
Yeah, but I don't think that arrow means anything.
It means it's the identity function.
Behaviors lead to behaviors,
Right.
which lead to a game. Sure.
Okay. So there are lots of ways that we could talk about this, but I think for the purpose of this class, I think the most interesting way to kind of get across mechanism design is just to give a few examples. So I'm going to give 2 or maybe 3 examples and sort of work through what is sort of easy and hard about mechanism design and try to give you a feel for why this is actually important and how by making little sort of specific decisions, you can have a huge impact on the behavior that people have. And in fact, you could argue that everything that happens in politics, the laws that we make, they're all about mechanism design. They're all about figuring out how to influence behavior. They're all about incentivizing particular behavior by people. So the big example that people talk about every 4 years when there's a presidential election and we're worried about, the budget is one of the biggest sort of mechanism design things implemented in the last several hundred years, which is the mortgage deduction. Right? So if you buy a house and you take out a mortgage, you get a huge deduction. And why is that a good thing? Well, because it makes buying a house cheaper, so it actually encourages you to buy a house. And we think that's a good idea for a bunch of reasons, but it doesn't even really matter why we think it's a good idea. We have actually constructed something to encourage people to buy houses.
Okay.
So let's see if we can kind of do this in the small and kind of think about how you might go about thinking about how you would generate certain behavior in people. Okay?
Sure.
Good. Okay, Michael, so here's the first sort of real example that I'm going to give you, and it's going to be in peer teaching, which hopefully is near and dear to some of our listeners' hearts. So here's the idea. The idea is that we've got a student, let's call this student Curly, and we've got a teacher, let's call this teacher Smooth, and there's a bunch of questions, okay, on some subject. Pick a subject you like.
Dinosaurs.
Dinosaurs. Okay, good. So
Yeah,
there's a bunch of questions on
You
dinosaurs.
should draw a dinosaur.
Okay. There, I've drawn a dinosaur in white ink. Okay, so what we have here is we have a bunch of questions about dinosaurs from
It's a
various
snow
things.
deinonychus.
A snow. Okay, let's try that again. So what we have is we have a bunch of questions, and let's just say for the sake of this discussion that we can sort them and order them from really, really easy questions to really, really hard questions. Okay?
Sure.
And what I really mean is that things down here, people with very little knowledge about dinosaurs could answer. People up here, you really have to have learned a lot about dinosaurs, and it kind of moves between the spectrum from easy to hard. Does that make sense?
Yeah, I guess as a coarse approximation.
Sure. And so what we're trying to figure out, and this is important, the goal here is to figure out what incentives we can give to both the student and to the teacher so that learning happens over time. So the goal is learning, and what we need to do is design a mechanism.
And mechanism in this setting means like a payoff function, essentially?
Yeah, because we're talking game theory, so in the end, we're always going to be talking about some kind of payoff, some way of providing utility for taking some kinds of actions in the world. Now, it's important, of course, this is not just simply a one-shot game. This really is a case that we will be taking actions over a period of time because, of course, learning is going to happen over a period of time. And we want to figure out how we're going to get someone to kind of give out these questions. This is all we've got, right? We've got a learner, we've got a teacher, we've got a bunch of questions. We know they're easy and hard, and we're going to try to figure out what we want the teacher to do and what we want the learner to do so that learning happens.
Yeah.
Okay? So we need to design a mechanism that will ensure the goal.
And just to be clear, is there assumption that answering questions actually helps you learn, or is this just assessment?
This is sort of assessment. This is assessment. But of course, if you can reliably answer questions, then it suggests that you know something.
Okay.
Does that make sense?
Yeah, I guess I'm just wondering to what end, right? So what kind of questions should be asked
Ones that help me to figure out that you've learned.
that you've learned?
Yeah.
Okay.
Now, other stuff can be happening here. And there's, whole complicated things. Readings can happen in between. There can be tutorials or whatever. But we're trying to make this game really sort of simple to illustrate the idea. So in between questions, things might happen.
Okay.
And perhaps answering the question requires that you go off and you do some reading or do some work,
Oh, which could promote some learning.
which could promote some learning. Some of these questions might be implement 5 supervised learning algorithms on 2 data sets that are interesting, run them, and write a 12-page essay, for example.
Oh my gosh, that's a terrible assignment.
Yeah, but you will learn something in the end
Yeah, you'll learn that some people give terrible assignments.
that cause you to learn. I think that's what's really important here. So are you with me to understand kind of what it is we're trying to accomplish here?
I think so, yeah.
Okay, cool. So let me give you a proposal for some incentives, and you tell me what you think is going to happen. So here's a proposal. I'm going to give a point every time the learner answers a question correctly.
That makes a lot of sense.
That makes a lot of sense. So you basically get credit for being right.
The learner gets
The
credit.
learner gets credit for being right.
Okay.
I'm also going to give +1 to the teacher. And for the teacher, I'm also going to give them credit +1 every time the learner answers correctly.
Good. So their incentives are aligned.
Yes, their incentives are aligned. The learner gets credit for demonstrating they've learned, and the teacher gets credit for demonstrating they at least know something. So what do you think is going to happen here?
The learner's happy getting answers right, and the teacher's happy when the learner gets answers right. So they should work together to maximize, I guess not necessarily learning, but ask easy questions. If you ask easy questions, then the learner wins and the teacher wins.
That's exactly right, I think. So hopefully that makes sense. So if, let's say, this question or questions way down here are so easy that anybody can get them right, then if I ask questions down here, the learner will get them right. So that's good for the learner. But also because the learner will get them right, that's good for the teacher.
Right, but that doesn't seem to really make sense for this problem in that we really want to be asking questions roughly at the level where the learner is.
Well, that makes sense. Well, let me ask you one other question. Before we get there, let me ask you one other possibility. Since this doesn't give us what we want, right? Basically, this says always stick to easy questions.
Right.
And we'll both do well. What happens if I say, oh, okay, well, the problem here is I've incentivized the learner in a way that kind of makes sense, right? Learner wants to get correct answer, get questions right. But I've incentivized the teacher to go easy on the student. So why don't I make it so that the teacher loses a point every time the student gets something right?
Oh.
So now the teacher is not incentivized just to give easy questions. What's going to happen here?
Well, part of me feels like it just seems like the right thing for the teacher to do then, from the teacher's perspective, is give hard questions. The learner should try to answer them, but the learner's not going to be able to answer.
Right. So what I should do is just immediately go to all the really, really hard questions about dinosaurs. You can't answer them. You don't have the background and, the sort of fundamental math and calculus to answer the questions about dinosaurs. And so you're going to keep getting them wrong, but the teacher is going to do just fine. And in fact, not only will the teacher lose a point every time the learner answers something correctly, let's say actually the teacher gets a point every time the learner answers incorrectly, which is sort of the same thing.
Yeah.
But allows me to say the teacher racks up points
Yes.
by making you do things that are wrong. Okay? So this is just kind of broken. Right?
Yeah.
The kind of obvious thing to do here, where I'm going to give the student credit for demonstrating they've learned things, they have knowledge, and give the teacher credit for either demonstrating that the student has knowledge or doesn't have knowledge, gives me bad answers. And in particular, it doesn't help me with the goal of learning. It doesn't help the student and it doesn't help the teacher. It just gives them whatever credit they're supposed to get when they can bother to get it.
Well, so if the teacher getting +1 for the learner getting something correctly ended up making things too easy, and a -1 made things too hard, then right in the middle is a 0. So what
Right.
about the teacher gets 0 for the learner answering correctly?
Well, the teacher gets 0 for the learner answering correctly, and it doesn't matter what the teacher does.
So maybe the teacher can do the right thing now.
But why? It's just like the cocoa example you're giving before. What reason do I have? And we certainly don't want the student giving the teacher side payment. Although,
Would that work in this case? No, because now the learner would want to get to maximize the side payments. Then we're back to the original problem that you said, which is if the teacher's paid off for the learner giving correct answers, then the questions are just going to end up being too easy to be meaningful.
that's right. And there's really no side payment for the teacher to give the student. But you said something earlier that I really like. You said, what did you say? You said something, before we went down this path of the -1 and getting hard questions, you said something about what the teacher ought to be doing.
The teacher ought to be asking questions, I don't know, so that the learner's kind of getting half of them right.
So I like that. So let's sort of take a step back and kind of see what that would sort of mean. Let's imagine that these spectrums of questions really do line up with not just easy and hardness, but actually line up with understanding, which is sort of the assumption that we made, right? That anyone can answer the easy questions, but as you know more, you can answer the hard questions. That means the chance of you being able to, the sort of these questions are aligned, not just in terms of easy and hard, they're actually aligned with some underlying notion of what you actually know, what your knowledge is, which I'm just writing as understanding here. Okay. Now, furthermore, let's imagine your understanding were here, okay? This is really where you are in this understanding scale.
This is where Curly is.
That's where Curly is.
Okay, in this linear scale of, knowledge.
Yeah, so this linear scale of knowledge about dinosaurs that apparently requires some background in calculus, you're basically here on this linear scale. Well, what would that mean for you to be right here? Well, it probably means that for questions way over here, those really are easy for you, and you'll always get them right. And for questions way out here, they're too hard for you, and you're probably going to get them, almost certainly get them wrong. But one of the interesting things about being right at some particular level of understanding is that you will occasionally get some of these things just on this side of your understanding right, and you will occasionally get things just on this side of your understanding wrong. Really, kind of understanding is like a probability function, and I'm going to pretend it's Gaussian because, that's what we do in machine learning, and just kind of say sort of the probability of you getting a question right depends upon where your understanding is. And as you move far in one direction, you will always get them right. Far in another direction, you will always get them wrong. But right around your level of understanding, there's some noise there. And you will sometimes get the ones that are just beyond your understanding right, and sometimes get the things that are just below your understanding wrong. We actually talked about this in the machine learning class, you might remember, when we talked about self-play and learning how to play games. Do you remember this?
Was a racquetball example?
Right. We used a racquetball example, and we talked about how if you play someone who is much, much better than you are, then basically you never learn anything because you always lose.
That's like the hard questions.
Those are like the hard questions. And if you play someone you're much, much better than, you also never learn anything because you always win.
That's like the easy question.
Right? And in fact, the right thing to do is to play someone who's just a little bit better or just a little bit worse than you, that is right around where you are, and then you'll actually learn something because the exploration makes sense, and sometimes you get positive feedback, sometimes you get negative feedback, and you learn how to modify your actions and to learn.
Okay, that makes sense to me.
Right, and so by analogy, that's what's happening here. If I can give you questions right around where your level of understanding is, then you might learn something.
Good.
So, given that highfalutin thought and taking it all the way back to racquetball, what do you think a good set of incentives might be?
I don't know. What I wanted to say was, well, you want to be getting like half of them right, and so we could pay off the teacher. Well, I guess we pay the learner off for getting things right because that's really what the learner should be striving for. But we can pay off the teacher for keeping things around a half. But that doesn't really make sense because then the teacher could do like, I'm just going to randomly choose from a really easy problem or a really hard problem, and on average that'll be a half. So it'll really not be asking any questions that are in that happy zone.
Oh, that's good. So actually, what you just said is pretty important.
And it seems like a really bad idea.
No, it's actually really important. You said something in there really important. So let me point out to what you said. You said that if I tried to pick a half, or any distribution really,
okay,
then the teacher can always just choose questions to kind of get that distribution. And sometimes they'll be incentivized to, I'll just pick easy ones or hard ones where I know I'm going to be able to get the distribution that I want.
Right.
And that sort of misses the point.
Yeah.
But what if I don't allow you to pick the question? What if instead I require you to tell me where this line is?
So the teacher isn't getting to pick questions anymore?
No, what the teacher's going to do is the teacher's going to say, here's where I think the level of understanding is.
Okay.
And then questions will be generated accordingly.
Ooh, maybe from a Gaussian.
Maybe from a Gaussian.
Okay.
And in fact, what I'm going to suggest we do is that we're going to say you need to pick a line. Now, why should you pick one line over the other? Because I'm going to set up the incentive so that you get +1 anytime the learner answers correctly something they should get wrong.
Oh.
But you also get +1 whenever the student gets something incorrect that they should get right. So what does that mean? So if you say, well, this is where their level of understanding is, what you're really doing is you're kind of picking two questions, right? You're saying, well, this is a question that they should get right, and this is a question they should get wrong. But if you've actually identified where their level of understanding is, then sometimes they'll get some of these things wrong that they should get right because they're easier, and sometimes they'll get right some of the things that they should get wrong. I sort of set up the problem that way.
Okay.
Right? And I'm going to get credit for that.
You're the teacher,
You, the teacher. I'm the teacher going to get credit for that. Well, let's see. What does that mean? Well, that means in order for that to work, I must have identified more or less correctly where your level of understanding is as a learner.
Because if you set it too high, the learner's always going to get things wrong, but there are things that the learner should get wrong, so there's no points to the teacher.
Mm-hmm.
And if you set it, the teacher sets it too easy, the bar down towards the bottom, then the learner's never getting anything wrong. And when it gets things right, it's things that the learner should get right. And again, should just means below the bar set by the teacher.
That's right. So you'll get some points by doing that, but you won't get as many as if you get it right where they ought to be.
So the maximum comes when you've done this 50-50 thing, right? Where you're getting points for the learner stretching a little bit, getting a little bit above and scoring well, and you're getting points for, I guess, tricking the student in a sense. Like
I would say tricking, but you really is you're sort of testing where their understanding really is, right? So if it's the case that if I identify this correctly, you will still get some things wrong that we would think you would get right, and you'll get some things right that we think you would get wrong. You really want to do it on both sides. And so if I move this line too far to one side, I only get points for one side of the bar. If I move things this far, all the way over to the right, I only get points for the other side of the bar. I want to get things for both sides of the bar. And so that's only going to happen if I can identify roughly where your level of understanding actually is.
That's clever.
That is kind of clever.
Did you come up with this?
I came up with this by listening to a guy named Jordan Pollock when he told me this is what he ended up doing with a real class of, I think, 5th graders.
Oh, interesting.
Now, by the way, there's something subtle here. We actually aren't finished with this. We just described this as if it only happens once. Really, what we did is we spent all our time talking about the teacher. And that makes sense because, the teacher has this complicated incentive function, right? So the teacher's going to get credit for basically identifying where your level of understanding is. So let's say I've done that. I know where your level of understanding is. I put the line here.
Good.
What's going to happen for you as a learner? Your goal is still to maximize your points. So how do you maximize your points?
From the learner's perspective, just try to always answer correctly.
Right. So how are you going to start answering things correctly? Getting more and more things right?
By learning?
By learning, by actually moving your actual bar to the right.
Oh, I see.
Because then you will not get these things wrong anymore, and you will get these things right. And so you will increase the number of points that you get.
Got it.
So then this will cause you to learn more so that you can get more things right. And then what's going to happen to the teacher?
Teacher's going to be unhappy? Well, the teacher could move the bar to the right.
Right.
To kind of catch up to where you actually are.
Right. So the learner is incentivized to learn, and the teacher is incentivized to understand really what the learner has learned. And they will keep pushing each other until you've learned everything.
Ooh, and then no one has any incentives anymore.
Yeah, but at that point you know everything, and you're a teenager.
Well, I was worried about this case where, so then the learner feigns ignorance for a little while so the teacher can move the bar down and then starts getting things right and wrong again. Yeah, I don't know. I guess that's not really a concern.
Yeah, I don't think so.
Okay.
And even if it is, the teacher will immediately figure this out, and the learner will be giving up points in the meantime.
Yeah.
That's not really the maximal policy. I mean, you'd have to get it exactly right.
Right. It's just that once the learner's learned everything, the teacher has no incentive anymore.
Sure, but then once the learners learn everything, then you're done. When the learner is ready, the teacher will appear. And when the learner no longer needs the teacher, the teacher will be killed by somebody, and then you have to go off and learn Kung Fu. It's very simple.
I think you're actually taking the plot of Kung Fu.
Yeah, I am.
Okay.
Well, anyway, I'd like to thank Jordan Pollock for this. I really love this example. That was really the first example of kind of mechanism design that really sort of hit home for me.
Nice. And it seems relevant to this kind of online teaching scenario that we're in right now.
Yeah, I mean, it's not enough for, I'm sure some people taking this class have actually done peer grading. And there is always this question of why won't everyone just give everybody good grades? You have to construct something so that doesn't happen.
Good.
Okay, so I'm going to give you one more example,
Nice.
I think, and then I think maybe we'll sort of cover the space enough. What do you think of that?
That would be great.
Okay. Okay, so here's another example of mechanism design, and I'm going to basically break it into two bits. I'm going to see if I can remind you of a particular mechanism design that somebody famous once used in a story told in the Bible, and then point out that that's kind of ridiculous, and then we're going to come up with something slightly better. Does that seem fair?
I'm interested to see this. Sure.
Okay, so this is the story of King Solomon. I drew King Solomon to look remarkably like Curly.
Oh, fun.
Yeah.
I get to be King Solomon, finally.
King Solomon. So do
after
you
all this time.
remember the story of King Solomon?
Yeah, he was wise.
Okay, let's go with that. So then tell me the story of King Solomon and the two women and the baby.
All right. So once upon a time, King Solomon was, hanging around on his throne doing kingly things. And he would answer questions for the various people in the country that he ruled, Judah, maybe?
Sure, let's go with that.
And but he was, he was known for being very wise, so people would come to him with very difficult problems. So one of the difficult problems was two women came to him with a baby, and each of the women claimed that the baby was her baby.
Yeah.
And they could not come to any kind of agreement. One of them, it was actually the baby. The other one was someone who really wanted a baby, couldn't have a baby, and then took someone else's baby. And so this is not the sort of thing you want to get wrong, giving somebody's baby to somebody who's not their mom.
Right. So let's see. So there are two women. We got to give them names because I'm having a hard time keeping track. So let's just call them A and B. A for, I don't know, Alice, and B for
Bob.
That makes perfect sense.
Wait, no, Beth.
Beth. Okay, so Alice and Beth, and then there's a baby. And so Alice comes to King Solomon and says, Beth stole my baby. And then Beth comes to King Solomon and says, Alice stole my baby. And then the baby just goes, gah, because that's what babies do. That's a little curly hair thing.
Oh, yeah, that's
baby,
cool. Yeah.
And now King Solomon does what?
So King Solomon checks whether the baby is named A or B, and then can actually trace the genetic roots of the baby back to the appropriate mother.
No, that was an episode of CSI. What does the story claim happens?
Yes, I'm sorry. So King Solomon says, all right, I've thought about this a lot, and I've decided that the only fair way of dividing up the baby is by dividing up the baby, giving half to A and half to B. And so that was what he claims he's going to do. He calls for his royal sword person to bring a sword, and he gets ready to cut the baby in half, at which point I recognize that royal sword person. It's a Jedi.
Mm-hmm.
All right. So the royal sword person says, okay, I will bring you the royal sword, and Solomon gets ready to cut the baby in half. And suddenly, woman A cries out, no, don't do it. B can have the baby. No. Yes. And so B gets to keep the baby.
I don't think that's what happened.
No, so then King Solomon says, aha, I set this up all along. I never really was going to kill the baby, let's say. And instead, what I wanted to find out is who really cared for the baby, this particular baby, and that would be the particular baby's actual mother. So the thought was that the mom would rather have the baby live and be with a different mom than be sliced in half, which would probably complicate the baby's life.
Yeah, actually, I think it would simplify the baby's life.
Oh.
But okay, I'm with you on that. Right. And then King Solomon could then determine that, in fact, A was the mother.
And, sewed the baby back up and gave the baby to A and sent B to prison?
I don't remember.
I don't know. Maybe he had a baby with B for B's sake. I don't know. That's not really part of the story in my head. At that point, A leaves with the baby, A's happy. B is disappointed, but not so disappointed because there's plenty of other babies to steal.
Right. And then, of course, there's the poor swordsman who didn't even get to cut up a baby. Okay, so this is...
He does look disappointed.
I do. Or he does, sorry. He does look very, very disappointed. Very sad. In fact, there's a single tear. This is mechanism design, right? King Solomon constructed a game with payoffs, which somehow are supposed to capture what's really going on with the mothers, and based on the action was able to kind of determine what their true preferences were. So really, this was a game about eliciting preferences. And in fact, that's exactly what you said. You said by their reactions, by their behavior, King Solomon was able to figure out that A preferred that the baby live and have B get it, him, let's say him, while B preferred mainly that A not have the baby. And by once getting preferences and saying, well, those preferences only make sense for the real mother and the fake mother, let's just go with that. And so now I can determine who the real mother is.
Okay.
Right, and King Solomon was wise. Now, I'm going to make a claim, which is that this is insane and doesn't actually make any sense. So let me ask you this, Michael.
Sure.
You're a rational kind of guy.
I'm a wise guy.
You're a wise kind of guy. You're definitely a wise guy. Let's imagine that you were B. Let's say B really is not the real baby mother, real baby mama. Okay, so
Okay.
B is not the real mother, but let's say that you're B, okay?
I want to be the king, but okay,
And
sure.
King Solomon, you can be both, and King Solomon makes this offer. I will cut the baby in half.
Okay.
If your goal is to keep the baby,
Right.
or at least to make certain A doesn't get the baby, what
Right.
should you actually do?
All right, here's what I think you want me to say, but I'm not sure that I completely get it. So B is as wise as King Solomon because game theory assumes we have rational agents, et cetera, with infinite processing power. So B is at least as smart as King Solomon. And so B says, okay, King Solomon's going to use whatever I say to decide whether or not I'm the real mom. And in particular, if I say don't cut the baby, he'll think I'm the real mom. So B will cry out, do not cut the baby. No. And now King Solomon's back where he started in that he has two identical women and two identical reactions.
Right. And so if both of them say no, then King Solomon knows nothing.
But A, being an extremely rational person as well, says King Solomon will know that the person who actually is not the mom is going to say no facetiously. And so only the real mom would say, yes, cut the baby in half.
No.
No?
No. Because if that were true, then the other thing then the story would make any sense.
Oh.
Actually, the story doesn't make any sense because, first off, the idea that someone would say, oh, you're going to cut the baby in half. I'm fine with that. As if people would be like, no, that's a caring mom. None of that makes any sense. But we don't have to go. We can just talk about game theory and pretend there's a little matrix here and go, the best action for both of them is just to both say no.
All right, wait. So you're saying King Solomon set up a kind of a mechanism design problem or set up a mechanism, and it was a flawed mechanism because if you understand the mechanism, you know the right thing to say is just no. And so then he has to flip a coin to decide who gets the baby.
Right. And then, you're doing pretty okay in that game. Certainly better than the alternative, which is to say yes. Think about it. If your action in some sense is either to say no or to say yes, either whether it's my baby or it's the other person's baby, the equilibrium here is sort of both. If the other person says no, there's no reason for you to say yes.
Right.
And if the other person says yes, then you should say no.
Right. So that's a dominant strategy.
It's actually it's a lot like chicken and dare.
Chicken and dare has this sort of thing where you want to be the daring one if the other one's the chicken. This is like everyone says no.
Yeah, okay, fair enough. But you basically both want to say no. There's no circumstances under which you want to say cut the baby in half.
All right.
That's awesome.
Yeah. The problem with this, of course, is that none of these people studied game theory. So they maybe hadn't thought things through and they were just giving their original reaction.
Well, I'm pretty sure that in the real world, even people who haven't studied game theory would know better than to say, sure, cut the baby in half. It's just not socially acceptable.
Let's go with that. I don't see anything better than this. But if you think you can out Solomon, more power to you.
Well, I believe that there is a way to out Solomon, and it really boils down to noting what Solomon was trying to do. What was Solomon trying to do?
Solomon was they had private knowledge of whether they were moms or not, and she was just trying to get them to tell the truth.
Right. And what he was trying to elicit in this particular mechanism was what their preferences were. So this sort of private notion of whether I'm a mom or not, sort of what was happening with what King Solomon was doing was this kind of assumption that each mom held the baby in sort of with some kind of value. So mom A, in this case, woman A, in this case, loves the baby and assigns some kind of value or utility to having the baby around. And woman B also has a value or utility for having the baby around versus having the baby end up with the other woman.
Right.
And in particular, there's a value of the baby to the true mother that is higher than the value of the baby to the fake mother.
Maybe. Okay.
And in this case, that better be what King Solomon thought, because otherwise, why would the fake mother be okay with cutting the baby in half?
Again, not necessarily okay, just not as horrified.
Right. Well, that means there's a lower value there.
Right.
So there's two values that are actually going on, and let's say there's a value of the baby for the real mother, and there's a value of the baby for the fake mother. And really the only thing that we have to sort of assume here is that the value of the baby to the real mother is greater than the value of the baby to the fake mother.
Okay. Which is also not so clearly a good assumption.
Sure, but it certainly drives what's going on with King Solomon here.
If value is like willingness to pay, it could be that B is really rich but isn't the mom, and A is poor and can't really pay very much. But okay, all right, let's just go with this. So
I mean, if
we want to know who wants the baby more.
right, who wants the baby more? What's sort of the intrinsic value of the baby
Okay.
to each of the women? And if you assume that the true mother cares more about the baby, that is, has the baby at higher value than the fake mother, then believing this to be true makes sense.
I'll take it, sure.
And if that's not the case, then we're kind of lost anyway. So we might as well go ahead and just sort of assume that this is true. And anyway, if the fake mom has that much money, she'll buy a baby.
But that's what she's trying to do.
No, she stole the baby.
Oh, good point.
Okay, good. So let's assume that we really believe that there's a value to the baby, to the real mom, and it's greater than the value of the baby to the fake mom. Okay?
Mm-hmm.
So I'm just going to assert another kind of mechanism that King Solomon may have used.
Okay.
And I want you to walk me through it and see if you believe that this is good, bad, or the same as what King Solomon actually did
In the story.
Okay?
Yeah.
All right. So let me write that out. Okay. So I've written down a sort of flow chart here
Okay.
of an alternative for King Solomon that's, I'm going to claim, better than what King Solomon actually did in the story, which is threaten to cut the baby in half.
It's certainly more complicated than
It's
cutting the
certainly,
baby in half.
well, you think it is, but maybe it's not. So I'm gonna read all this
it
to
is.
you,
Uh-huh.
and we'll just kind of go through it, and you'll see if you understand. Now, remember, we're starting out under the assumption that the value of the baby to the real mother is bigger than the value of the baby to the fake mother.
Okay.
Okay. Now, here's step 0.
And again, value here is like willingness to pay,
Yes.
but we're just gonna go with that.
Yeah, we're gonna go with that. So here's step 0. King Solomon is gonna choose a fine.
Okay.
We'll call it F. That's greater than 0, but meant to be small.
Okay.
So, something like $1. Now, what do I mean by small? I don't just mean something like $1. I mean, F needs to be greater than 0, so there needs to be some cost to this fine. But it should be smaller than either of the values V real or V fake.
Okay. So V real bigger than V fake bigger than F.
That's exactly right.
Okay.
All right. So King Solomon picks a fine. And by the way, tells the two women this entire process that I'm going through now. So none of this is a surprise. They both know this is what they're going to have to go through.
Okay.
Okay. So King Solomon picks some value F. Then in step 1, King Solomon asks A, is this your child? If A says no, then B gets the child. If A says yes, then King Solomon turns to B and says, is this your child? If B says no, then A gets the child. If B says yes, then King Solomon,
So somebody's lying at that point.
someone is lying, King Solomon's not having any of it, and tells A that A will pay F.
Wow.
Okay.
Harsh. Okay.
And then requires that B announce a value V, some number V, that is greater than F. Okay?
Okay.
Then in the next step, King Solomon turns back to A and says,
How about now?
yeah, how about now? Is this your child? And if A says, no, it's not my child, then B gets the baby, but has to pay V.
Whoa.
V dollars.
Okay.
If A says yes, then A gets to keep the baby. A has to pay V, and B has to pay F.
Okay.
And I'm going to claim that this is better than claiming you're going to cut the baby in half, at least in eliciting true preferences.
Interesting.
Does that make sense?
It's intriguing.
Well, so,
I mean, it feels weirdly asymmetrical.
well, it is in some sense asymmetrical, but that's because their underlying values are asymmetrical.
No, I mean, at the end of the day, either A or B got the baby with no fines if somebody fessed up early. If they make it past the you guys are arguing stage 3, then one possibility is A pays the fine
Yeah.
and B pays V and gets the baby. The other possibility is that A pays the fine and A pays V and A gets the baby and B pays F.
No, if King Solomon tells A they're going to pay the fine, if we get down to here, A instead pays V and B pays F. So A doesn't pay F plus V.
Oh,
One of them's going to pay F and one of them's going to pay V.
Okay. That feels more symmetrical. Sure. Okay, good.
Okay. So how would you convince yourself of the veracity of what I'm suggesting, that this will do a better job of eliciting true preferences of the mothers?
I guess I would
purported mothers.
think through what the different, ways the game can play out might be.
Okay, cool. So we're going to go into the assumption. So let's see. One of these mothers is real and one of these mothers is fake. So, well, I mean, I suppose it's possible that they're both fake.
Oh, let's not go there.
Yeah, let's not go. That's not allowed. One of them's real, one of them's fake, because this is King Solomon and not King M. Night Shyamalan. Okay, so we're gonna do that, and I want you to figure out what would happen if we got all the way down to step 5, and A is, let's say, the mother.
Okay.
So what would happen in step 5?
A gets the baby.
A gets the baby.
A pays V and B pays F. So
Right.
F is the basically a penalty to B for lying,
Right.
and A is sort of a penalty to A. But it should be, well, it depends on how much B sets the value V for.
Oh, that's right. So what would B set the value V
Okay.
for? What are the possibilities?
Okay, it could be like $1 million, right? So that would definitely discourage A from saying yes.
Okay, so I say you picked $1 million because you think $1 million is more than the value of the baby to the real mother. Is that the idea here?
Yeah, I guess so.
Okay, so some value V greater than V real,
Okay,
which for the sake of this discussion, let's say is $1 million. Okay,
excellent.
so I'm going to claim that B would never do that.
B would never. Oh, so the disincentive for B for that is that A can be like, you know what? I can't afford a baby at $1 million. It's more than the actual value of my baby to me. You get the baby, but you're going to have to pay the $1 million.
Right, now, that's not just something that could happen, that's something that would happen, right? Because
Right.
we've tied everything up in the value. So if V is bigger than V real, then we get down to here and ask, is it your child? A will say no, because paying V for the baby is more than what the baby is worth. And so B will get the baby, but B will pay V. And what do we know about V? V is bigger than V real, which means it's also bigger than V fake.
Got it. So okay, so we're assuming that B has a value of B fake.
Right.
So
Or in this case, we're assuming A was the real mother and B was not.
A was the real mother and B was not. Yeah.
That's what I said,
right.
right? So B has a value of V fake. So then what value of V would B pick?
So B shouldn't be willing. I mean, B doesn't want the baby for more than V fake.
Mm-hmm.
That's how much B values the baby. And if B suggests a value V or announces a value V in step 3 that's bigger than V fake, B might get, B is at risk,
Right.
of getting the baby and overpaying for it.
Right. And having to pay more than
Economists
it's
are
worth.
weird.
Economists are weird. But that's okay. So that means that not only will B not pick something bigger than V real, V would not pick anything bigger than V fake.
Yeah, and in fact, in principle, B would rather pay up to V fake to get the baby. Anything
Right.
less than that, and if B doesn't get the baby, B is going to be sad for not having offered more. So at the end of the day, B is going to pick V fake as V.
Okay, so if B picks V fake as B,
Yeah.
then what do we know is going to happen at this question when A gets asked if it's your child? A's going to say yes.
He's going to say yes because
Why?
because if the value that B announced is V fake, and A is would have regret for not getting the baby. For not getting the baby and not bidding up to V real. No, bidding is probably not the right word, but
Let's go with it.
kind of suggesting or being. A would have been willing to pay up to V real for the baby, so A would be happy to pay V fake for the baby.
Because V fake's less than V real.
Yeah.
So A will, in fact, say yes. A will get the baby, will pay less than the value for it. And what happens to B?
What happens to B? B pays a nominal fine.
Right, but that's greater than 0.
Oh, so if they both thought this all the way through,
Mm-hmm.
now we can unroll back all the way to step 2,
Mm-hmm.
where B is asked, "Is this your child?" Now B is saying, "I could say no," and A gets the baby, and I just walk away.
I get 0.
Or I could say yes, and I'm going to end up paying a fine.
Right. So,
and another but at least A is going to have to pay a lot of money. So
but it's all built into the value here.
all right.
So that means that since B is never going to be willing to assert a V greater than V fake, which means that B is never going to be able to make it so expensive that the real mother would say no, B has no reason to ever let it get this far because B will pay something. B will get minus F, which is less than 0, which means if we ever get to step 2, B will bail and say no.
I see.
Now, what if A is actually fake and B is real?
But that's not the truth.
It could be the truth. We didn't know that.
All right, we want the mechanism to work either way.
That's right.
Okay, so all right, so let's go to the bottom again. So if B is the real mom, B has a value of V real, which is bigger than V fake, which is A's value.
Mm-hmm.
So when B announces the value,
Mm-hmm.
B probably should announce V real
Mm-hmm.
because, again, B is going to want to spend that or wouldn't want to not get the baby having not spent that amount, right? Would have regret for that. And so B is going to basically be truthful, right? And say what B's true value is, which in this case is V real. At that point, A has a choice. A can say yes and is going to have to pay more for the baby than the baby's worth to A.
Because V real is bigger than V fake.
Or say no and walk away having paid the fine, but B gets the baby but at a very high price.
But it doesn't matter because F is still bigger than 0.
I see. So now what you're saying is, so that is a little bit weird and asymmetrical, right? So B gets the baby for V real, but if it was A who had the baby, then A is going to get the baby for V fake, which is less.
Right. But it doesn't matter. The point
But
is
your point is that because of this fact, because of the fact that if A lets it get this far, knowing that A is not the mom, it's going to cost A the fine.
Right. And A will not get the baby. So that means A doesn't want it to get this far, which means when asked the question, having thought it all through, A will just say no. So in fact, by saying this is the process we're going to go through, when asked the question, both will be truthful.
In fact, all the questions will be truthful all the way up to question 1.
What?
All the questions, so any question that's asked is going to be answered truthfully by this design.
That's right. I'm sorry. You were saying all the way up to, you're going counting backwards. That's right.
No, well, I see, up to 1. Yes, up the screen to 1.
Right. So, yeah, that's exactly right. Without knowing what V real and V fake are, but with everyone understanding that the baby is valued more by the real mother than the fake mother, this mechanism is set up in such a way that it makes no sense for the fake mother, whoever it is, to ever let it get this far, ever let it get to step 3. So as a result, when forced to ask the question, the fake mother has to bail.
Got it.
Before it gets to 3, because otherwise fake mom will lose.
Clever.
Therefore, this mechanism will in fact elicit the true values of the baby and will allow King Solomon to know the right thing. Because of this, King Solomon knows that they will answer truthfully and will find out who the real mother is.
Neat.
And the only person who loses in this is the poor person with the sword.
Oh, again.
It's kind of sad, isn't it?
So sorry.
And there you go. So I think that that's a pretty interesting example of how you might kind of do mechanism design.
That is really interesting. Yeah, and so I slipped and called it a bid at one point because it sort of reminds me of what people do in auction design.
Right.
So when auctions are designed, it's often the case that you want to set up an auction so that people reveal their true values for the goods that are available, and that that they'll bid their true values, and that the winner, the one who values it the most, will actually end up winning at the end of the day.
Right. You try to set up a structure so that people will basically pay what it is they really want, or at least will announce what it is that they really want. There are lots of variations on this. And in fact, some version very similar to this is sort of what eBay does, but without babies. But the baby in this case is the prize.
eBaby.
eBaby.
Wait a second.
We have a website. Let's go get rich.
No, that's not. Oh, I think that's illegal.
I think it depends.
But I was just going to say that if you switch the A's to B's and the B's to A's, then eBay is baby.
I do not understand how you do stuff like that.
Oh,
but I'm impressed.
All right.
Okay, so here we are. So yeah, auctions. And by the way, you might think that this would be a natural segue to talking about auctions, but that'll be our third class that we'll never actually do. Seem fair?
At least we're being honest. We're bidding our true values.
That's true. All right, so with that, there are lots of other examples that I could come up with and we could talk about, but I think that I think I've sort of made the point here.
Yeah, that's really neat. I mean, again, it feels, not to be dissing on my homie King Solomon, but namesake.
Mm-hmm.
Isn't that what homie means?
In Yiddish, yes.
Okay, fine. So, but again, if B is rich enough, B is just buying the baby and not even paying A appropriately for the baby.
Well, if B is rich enough, B probably just bought a baby.
Yeah, but bought the baby for the for what? For the for B's own value of the baby.
So it has to be the case that V real is greater than V fake, or all of this fails.
Yeah.
But let's just say it is.
No,
if
but
it's not, then we'll come up with some other design. And actually, by the way, there are mechanisms for solving this where you don't know what it may be the case that fake's greater than real, but you sort of limit the possible values that each might get. You kind of think there's like a distribution of them, and there are clever things that you can do to sort of make this work, but well beyond the scope of this single slide, which we've done all of this on one slide. So it's well beyond
All of this and a little more.
Yeah, there's just no more room on the slide, so I can't talk about it anymore. All right. So I think, speaking of game theory and true values, we have a problem.
All right, what's the problem?
The problem that we have is that we've now come to the part of the lesson where we have to say, what have we learned? And one of us drives and the other talks.
Great.
But we both did things in this lesson.
Oh.
So I'm going to say that we kept switching turns. In order to make parity work, you should do the what have we learned.
All right, so what have we learned? I think you basically convinced me to do the writing, and now you're the one who has to actually think about what we learned.
No, what we'll do is we'll end up sharing. So you tell me what we've learned, and I'll tell you if that's right.
So there was Game Theory 1 and Game Theory 2, and they had their own what have we learned along the way, right?
Right.
All right, so then what happened when we came back? There was Scooby-Doo noises.
There was Scooby-Doo noises.
Then we talked about
solution concepts.
Exactly. And we focused, we listed a bunch, but we focused in on 2 of them.
Right. And I talked about correlated equilibrium and the relationship to Nash equilibria and sort of how they're awesome and efficient to learn or efficient to compute.
What was the main idea of correlated equilibrium? What was the thing that was introduced that makes it work?
Traffic lights.
Better known as a shared source of randomization.
Yes, which I don't think I ever actually said. But yes.
I heard it implicitly.
Yeah, it was implicit. A shared source of randomization. In other words, that 1/3 that we did with the cards was something that we both knew that kind of allowed us to correlate possible outcomes. And that is, again, a shared source of randomization. And I think even convince you that traffic lights are a kind of randomization from your point of view when you get there.
So it ends up being an easier solution concept to find the values for, but it also is it requires more power. If you don't have your source of randomization, you can't even use this.
That's right. But it is powerful, and it allows us to often come to a better outcome than we would with the Nash equilibrium.
For some definition of better.
Higher expected utility.
For both players, for one player, for the average player?
Well, it'll depend on the game.
And I think it generalizes to arbitrary number of players, but the game matrices themselves get really big as the number of players grow.
But that's true anyway.
Yep, exactly.
Okay.
All right, and then I talked about a solution concept called cocoa values, which had an even stronger assumption, not just that there's a shared source of randomization, but there's actually binding side payments.
Mm-hmm.
Meaning that there's a mechanism for deciding who gets what once the actions have been taken and utilities have been distributed.
Right. And this encourages a player who might not have a reason to do any particular equilibrium to pick one that is beneficial to one of the other players because that person will share in the increased benefit.
Right. So it encourages a Pareto optimal response. That is to say that in particular, they're going to choose the outcome that has the largest total reward, and then they're going to divide up that reward.
Did you mention Pareto optimal when we were talking about this?
No.
It was implicit, much like shared source event randomization was.
Both these algorithms, it turns out, have been used in the sequential games setting, the stochastic games.
Yeah. Well, solution concepts are usually useful in all those things.
Yeah.
Oh, you should mention one other thing, which is we actually pointed out that something that we talked about last time was in fact a solution concept.
What, Nash?
Nash and?
Oh, subgame perfect.
Right. By the way, worth pointing out that the King Solomon alternative that I described before is subgame perfect.
Oh. All right. Well, so let's flip over to that, which is mechanism design. We talked about
2 things in particular. We talked about peer teaching.
Right.
And we talked about King Solomon.
Dividing up babies.
Baby division. Never, ever divide by 0. Now, what's interesting about mechanism design, sort of the flip side or complement of what we normally think about in playing games, is that one could look at a lot of these solution concepts as, in fact, being mechanism design. Right? You create cocoa values as a way of encouraging certain kinds of behavior by setting up binding side payments. You think of correlated equilibria as working because you've created a mechanism, this shared source of randomization, that will encourage behavior that it wouldn't otherwise encourage. Therefore, all these solution concepts can be thought of, sort of, at least all the ones beyond the kind of obvious one of Nash equilibrium anyway, I have to think about that, can be thought of as a kind of mechanism design. These extensions, these things that we introduce are to induce certain kinds of behavior. And so even if we didn't want to think too hard about mechanism design or wanted to believe it wasn't really a part of reinforcement learning, it really is, because all of these things that we come up with as these sort of extension solution concepts are really about getting better outcomes.
And they're all about driving behavior using rewards.
Right, which is so much better than driving Miss Daisy. So I think that's everything that we've learned. Okay, so what's next?
I think we're done, actually, with the material. We have kind of a wrap-up that we need to do, like an outro. And so, so we're getting down to the near terminal state.
Nice. Well, I think that's good. Well, this has been fun. I mean, I guess I will get to see you again after this, because we do have a few things that we need to do. But I think we've covered all the material.
Wow.
Well done. Well done.
All right. Well, good job, everybody.
Yeah, good job. I guess I will see you later, Michael. Bye.
Bye.